Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So in this video we are going to look at noise reduction. Before we get into noise reduction, we have to first talk about the model of a noisy image. So given that image G, there's a given image G, and we assume that it's actually the sum of the noise-free ideal image F plus N, where N indicates the noise. So this is called an additive model of the noise, where and it's also stationary in the sense that the noise is the same distribution everywhere. So that's the typical assumption that you would make. So it's called a stationary additive noise. N is zero mean noise. Okay. And the idea of noise removal through linear filtering, the first step we'll consider is linear filters. The idea of noise removal through linear filtering is basically estimating the expected value. So basically, what is the average G at every point, right? G is an image, so at the image as a whole, we are kind of estimating, and we can do that because since the expectation, if we take the expectation on both sides of this expression, so G is equal to F plus N. So if we take the expectation on both sides of this expression, then E of F plus expectation of N. So expectation is distributive across addition, then we can just say expectation of G is the same as expectation of F, expectation of N being 0. Okay. So how do we do this expectation? That is basically how do you do this expectation of G? So we make some assumptions about F. Okay. So what are these assumptions about F? Okay. F is locally constant or smooth. Okay. Locally constant is the better. Okay. And in which case E is estimated by neighborhood averaging. Okay, and if you look at something called median filtering, which we'll look at the subsequent lecture, it's basically if you take a large enough neighborhood, then you're assuming that the pixels are Gaussian distributed or normal distribution, right? Which is what we call it, right? And there's also some assumptions about the edges, and they assume that the edges are straight. Okay, but that's median filtering. In general, linear filter, big assumption is F is locally constant, so that you can estimate the expectation value of G by a neighborhood averaging. So we'll see what that means in the later slide. Okay. So one thing that you're all familiar is called the Boxcar filtering. Okay. So if you have an image, we take a very small patch of that image, and we assume that in that patch all the pixels should be of the same value. So then we replace the center pixel of that patch by the mean of all the elements in the patch. Okay. So one other thing that we can also do is to take into account that the likelihood of the image F having the same value as the center pixel decreases as we move away from the center pixel. So we can weight the pixels using a Gaussian distribution as a function of distance, right? But then Gaussian distributions are infinite support because, in the sense, Gaussian distribution, if you take the continuous distribution, it's defined for all values of the input x, right? Let's say, and so since it has, that's why it's called infinite support. So it's there for all values of x. So for implementation purposes, we have to cut it off in the neighborhood. Okay, and implementation of all of these linear filters can be done in a Fourier domain. So you take the Fourier transform of the image, Fourier transform of your filter function, which is in this case, for instance, Boxcar averaging. It's all just bunch of ones with a normalizing factor, or Gaussian function, which you can Gaussian weighting function, which of course it's Fourier transform is also a Gaussian. So there are different filters in the Fourier domain for filtering and for noise. For example, denoising. Many of them are just low pass filters. That is, we assume that the sudden fluctuations in a small neighborhood, that is occurring only due to noise. and so that conforms to the high frequency components in every image. So you cut them off by using low pass filters. So for instance, Butterworth, Hamming and Hanning windows, not hand windows, sorry, Hanning windows. They are some of the more commonly used things for image denoising. Okay. But I'm just going to have to make sure you understand what we mean by this linear filtering, Boxcar averaging, etc. Okay. So I'm going to do some hand-on examples. So for instance, you can consider some box. Okay. Let me see here whether we can draw something reasonable. Okay. This is the image. Okay. So we can draw a bunch of lines just to get the trying to get some lines are not there. Interesting. Okay, we'll just use the pen. Okay. Right. So we'll use this pen to get some lines in. So what we mean by expectation, basically the boxcar averaging filter is, let's say you take this pixel. What you do is you assume that in a small neighborhood, this is the assumption when you do this kind of filtering to remove noise. Okay, the small neighborhood that I got with this red box, you assume that in that small neighborhood, all the pixels are the same value. So how you might ask, how is this valid? So for instance, if you're looking at a particular type of tissue, or in this sense, let's just take natural images. Let's say you've taken a picture of a sky, and if it's a clear sky, it's going to be uniformly blue. So wherever you move across, if you look, in fact, the pixels corresponding to the sky, you expect all of them to be the blue color, which is the same RGB values. So similarly, in grayscale images also, let's say for medical images also, there are regions which correspond to similar tissue, and you would expect that pixel which corresponds to which lie on the similar tissue should have similar values or same values. That's their logic. So, but then you cannot do this, take this too far, because there are going to be some heterogeneities and they get worse as you move away from the center pixel. That's what we're going to look now. So we can see that in this 3x3 neighborhood, we can assume that this pixel is going to be similar to all the others. So then instead of, so one thing we can do is we can just, the easiest way would be to replace this by a neighbor, but in order to get some more statistics, we replace it with the average of all the pixels inside this region. Okay, and first we can move this box around, center it at every pixel, right? Center this box, red box at every pixel, and do the same, so that you get very good averaging. So you can see that this will remove noise, because it just smooths over the small fluctuations in the image. Okay, but it does do something bad, because you can imagine that this will actually blur the image. It's called blur. So sharpness will go away. Edges might lose. You might lose edges, or edges might be lost. Okay, edges might be lost. So this is the danger of that happening with this kind of a smoothing operation. So that's what people do, would be they do this Gaussian weighting. What you do is, instead of weighting it similarly, so what you're specifically doing is you're weighting each one of these pixels the same way. That's why you're replacing an average. But rather you can just put a Gaussian on top of this, a 2D Gaussian on top of this, so that each pixel will be weighted slightly differently, because as you move away from the center pixel, you want to weight differently. So you can actually choose a larger region, but you would weigh the, so for instance, to a different color, just to highlight. Let's say you choose a slightly larger green region, and let's just here, right, for let's say this pixel. So as you move away, as you move towards the edge of that region, then you would weight it considerably less. So that weighting can be obtained from a Gaussian, and you have to discretize the Gaussian, etc., in order to get that weighting. Okay. This is typically what you would do. If you look at this red box, it has 9 pixels inside it. So one picture, if there is an edge running through it, it will preserve the edge, because it's going to sort it, and it's going to come kind of, there will be some lowering of the intensity, but overall it's going to be there. So before we go, the next filter, which is not a linear filter, the previous one was a linear filter. This is not linear, this is a non-linear filter. It's called median filtering. what it does is, we saw this, right? It selects the center pixel value from a sorted list of pixel values in neighborhood. So it's the same as before, except that in a 3 by 3 neighborhood, so in this case, what you do is you take 9 pixels, you sort them from in increasing order, and you would choose the middle one among it. Okay. So what this does is it removes intensity outliers. Okay. And so since no averaging is done, it removes the intensity outliers because you are choosing the median. It will preserve edges. Okay. That you will see if you can. If your box actually straddles an edge, that the red box that I showed you. So the median filter preserves edges. It might sometimes remove so-called corners. Okay, there are some examples in several textbooks. I'll put them out there in the forum or maybe in a later lecture. When we summarize these few weeks, I will have a look at what median filtering does in detail. But median filtering, the implementation is very simple. You select the region. You sort the pixels in that region in increasing order, you select the middle one from there. Okay. Since you are not averaging, very large outliers are easily removed, and this actually is very good at removing something called salt and pepper noise. So some random high pixel values or random low pixel values are easily removed, and you don't lose the edge as much since you are doing the sorting and then choosing the middle value. Okay. So the next couple of topics, they are slightly more complicated than what you have seen so far. So what you've seen so far are just one-shot techniques, right? You choose a region, you average it, replace the center pixel in that region, or you replace it with the median. We looked at how to take gradients, etc. Those are fairly simple methods. So the next couple of methods, one is the diffusion filtering, the other one is the Bayesian estimation. They are both slightly more complicated. They are what we might call iterative techniques. Okay. So we will look at them in the next few lectures. Thank you.